and thus I have a much simpler design than Andy Carroll's. It's not pure Lego solution, but it's actually much closer to the way the original works. So these were my first pass at designing custom gears. So these are designed in a CAD tool chain, and these are rendered. These are, prefabrication. And I thought they looked pretty good, and they had triangular teeth, which is not really what Lego teeth are, but it would give me to see whether it would work or not. And, and I was just, figuring it out. I'd figure out the tools, had to figure out how to 3D print it, the whole 9 yards. And so I had to design 2 19 tooth count gears, 1 47 tooth count gear, 1 27 tooth count gear, and 1 223 tooth gear. The larger one here is the 323. The next largest one, which you can see over there on the left, is the 127, and then you can see the 47 and the 219s. I got them back from 3D printing, and I had a little problem or issue. I got myself a expensive plastic potato chip. My design had too much stress in it, as it cooled off from being hot, and not enough support in the Z-axis. So as it turns out, I didn't want to just throw this one away. What I did was I weighted it down with plates in my sink with the heavy weight on top of it, and used a lot of boiling water and gave it 6 hours in a steam bath and relieved its stress enough to make it be useful. And I built this mechanism. It's the same PDF files that Andy Carroll used, and I designed and built this, and you can see it is only 2 sheets wide. His is like 3 because it's got a whole center section, and his is just as deep as it is tall, deeper in fact, and mine, as you can see, is very much smaller, and all the gears pack in. This is much closer to the original. It's bigger than the original, but my Lego teeth are 3 times bigger than the teeth that the ancient Greeks used in the Antikythera mechanism. So I have an issue with my gear teeth as well in that first design. They worked, but they're triangles, and they don't actually mesh properly with Lego gear teeth. Now, Lego gear teeth are like modern gear teeth. All modern gear teeth have the involute shape of the gear tooth curve. The involute shape of the gear tooth curve is again one of those things that wasn't so much as discovered as it was observed. If you made some crude chopped off squarish tooth and knocked the corners off to kind of roughly bevel the tip, and then ran it for 10 years or dumped a bunch of sand in it and ran it for 2 years, your gear teeth would turn into this surface, because this is the constant force applied curve, the smooth touch. If you have anything other than this curve, the gears wear on either gear until they have this curve. And so this is the curve that gear teeth have to have. It's specced with an angle and a pitch of the teeth. So you can see the constant force application. You can see where it hops up when the tooth gets tied. So I wanted to have the gears I was going to print be fully Lego compatible. And that's not what the original mechanism has, but this is to work seamlessly with Lego and have as much accuracy as plastic parts can have. So here's a render, a 3D photographic render of a 47 tooth gear and a 19 tooth gear, what I'm going to print. And you look at this, and I got a transparent, what's called a brick arm, which has got the holes in it to run axles through. And you look at this, and an astute person will look at this and they'll say, okay, Kurt, I have 47, 19, that's all good, but how did you know it was going to go 1, 2, 3, 4 holes over and 1 down? How did you know that it was going to fit that way? And that's a good question. And so we're going to have a little lesson on gears. And this applies to Lego gears, but it could apply to all gears except for the absolute number. The rolling diameter of a gear is the diameter of an idealized disc that allows it to roll on an equivalent idealized disc of another gear that it's normally meshing with. They don't have to be the same size. But you remember this picture over here? The arc lines in the middle of the teeth, you see where these two arc to the left, arc to the right, go right through the center there? That's the idealized disc. It's halfway up the tooth. That's the idealized disc that's meshing. So when you talk about a rolling diameter of gear, it's the diameter of the idealized disc that allows it to mesh with the idealized disc of another gear that it's normally the teeth are meshing with. The rolling diameter in millimeters of any Lego gear is the same as the number of its teeth. Given that the circumference of a rolling disc is pi d, where d is the diameter, and if d is the same as the number of teeth, a tooth takes up pi d over d, or pi millimeters. Lego gear teeth are 3.14159 millimeters long. Most Lego technic people don't know this. It makes it very simple for kids to use Lego gears because they don't have to count. They don't have to think about pi. They can just add them up. So I make spreadsheets that allow me to compute, and I can plug in a 47 and a 19th. You can see the number of teeth of the two gears, and it calculates the distance over and the difference, because from the rolling diameters, it figures out what that distance has to be, and it says it's got to be 4 1/4 to mesh correctly. And then it finds what meshing with half stud boundaries for the holes, and it discovers if you go over 1 and down 4, or over 4 and down 1, there's a green highlighted one, and that is a highly accurate meshing distance for that pair of gears with that tooth count. That's how I know from my design how much space I have to lay out in my clock design. The CAD tool chain I used is all free. It's the ldraw.org normal Lego CAD tool chain, which is MLCAD, the editor, LDView, which is a viewer. The viewer can also output an STL file. That's a stereolithography file for 3D printing purposes. LPub allows you to make instructions, and the beautiful picture that I rendered comes out of the POV ray trace renderer. I also use the OpenSCAD 3D programming modeler. You can write programs to generate 3D objects. That's not Lego specific, but I can do Lego things if I just plug in the Lego standard numbers for things, so that I can make things that are Lego specific using that programming method. It allows you to do cylinders and subtractions and merges and ors and intersections. I also use 3D Builder, which is a 3D editor to check things. I use stereo to DAT to take stereo files and convert them back to DAT files, so I can go back into the Lego ldraw tool chain. And I use Mixer to find my errors. You have to have all your surfaces be smooth and no gaps. And so frequently you think you've figured out how to design your thing. Somewhere you've got a pair of lines that aren't touching correctly, and you have holes in your balloon, if you want to think of it that way. So why am I doing all this? I wanted those pin and slot mechanisms. I wanted to have the pin and slot in my design. These pin and slot mechanism in the original and the pin and slot mechanism in my design does the non-constant angular velocity of the balloon. So what is that? Well, okay, sorry. My original design, I only did 4 gears. I only had to design 4 parts. I needed 2 of the 19 truth counts to go on to produce the one with the non-constant angular velocity that Andy didn't do. I needed more custom gear designs and a couple of extra parts for offset axles and a longer coaxial tube. Many of them I needed 2 of those designs. So I ended up making 10 individual model designs and getting them correct. This elliptical epicyclic gearing on the 223 tooth gear, This is where the pin and slot gears reside. They are, in my drawing here on the right, you can see there's two gears stacked on top of each other. On the left, you can see the actual, the back of the mechanism, as you know, a good photograph of it from that's in the Athens Museum. And those look like two gears, but they're actually two stacks of two gears. And the pin and slot is visible down in the bottom one. So again, what is that why is it epicyclically mounted on this 223 tooth gear? The epicyclical mounting is allowing for the lunar epsidial precession. This is, the moon doesn't, like a spirograph around the Earth, it doesn't retrace the same circle. It precesses over time. It takes 8.85 tropical years for the moon to precess a full circle around the Earth. This would be, subtract the sun, center the Earth, watch what the moon does, and the moon's orbit precesses around the whole 360 degrees at the rate of 8.85 tropical years. This is called the lunar epsidial precession. That epicyclic gear calculates that effect. Otherwise, your eclipses get in air. They don't come out correctly. So I highly recommend you watch the Nova. A lot of this was going very fast, but what we're going to do is we're going to visit a lecture by Dr. Freeth. And Dr. Freeth gave an excellent talk about this at Stanford University. And they even say in the talk that this is the very first mathematician to give the university's lecture on ancient history, archaeology, which a mathematician gave the endowed archaeology lecture at Stanford University. It's a hoot. I highly recommend you watch it. We're going to watch some sections from his as he explains the gearing calculations associated with the mechanism. Because Andy did just the constant angular velocity of the moon, and he did the Saros dial and the calendar dial. He did the 235-month Saros cycle dial, and he did the calendar dial with the sun and moon pointers on it. So we're going to watch a little bit of Dr. Freeth's talk. Here, we're going to go over here, pick this up, and we're going to cut into his talk. I recommend you watch the whole talk, especially if you're interested in this, but we're just going to cut to some rather complicated math. And I had figured this out in the process of designing mine. So if I'd have known what this was about, if I'd have known this would happen, I would have flown out to California to hear this talk. I found out about it about a month or so later, and they had put it up on the YouTube, and I watched it. And my wife will tell you how excited I got watching this, because I was dancing up and down that, you know, I read their papers. I was trying to read between the lines to figure out how to actually build this, because I'm literally staring at these parts trying to figure out how to do it. And I basically figured it out correctly. And watching Dr. Freeth confirmed that everything I figured out reading between the lines of their papers, because they didn't clearly state exactly anything. I think that it was the consensus of understanding that emerged after a lot of those papers were published and before some of the final papers were published. So we're going to watch Dr. Freeth here a little bit.
Dial is an eclipse prediction dial. I had the glyphs and this index letter system. I can't go into the whole system, don't have space. If you're interested, you can Google Antikythera and +1, that's Public Library of Science 1, and it's an open access journal, anyone can read it. I just say that this is a prediction scheme of quite astonishing ambition. The index letters, you look at the index letter in the glyph, you look at it in the inscriptions, and that tells you characteristics of the eclipse. It's an extraordinary scheme. But going back to late 2005, what I wanted to know was, how was the pointer turned? Like Michael Wright had determined how the pointer was turned for the upper dial. So we need to go behind the plate and look at the gearing. That's all the gearing we saw for Michael Wright's gearing for the metonic calendar dial. And I want to turn the lower back dial. And again, I've suppressed the main plate so you can see the gears, but there's really only one axis which can turn this, and that's this little axis M. The gearing branches here to the upper back dials and to the lower back dials. And I need a gear with 223 teeth. It's a prime number, can't break it down into smaller gearing. And if you look at the back of the main fragment, fragment A, there's really only one good candidate gear, E3 there. It's not the ring gear inside it, it's the bigger gear, slightly harder to see outside that. This is the gear that Price called E4, and the Caracolos family counted as 222 teeth. Price rejected the idea that it was the 223 months of the Saros cycle. But if we look in our X-rays, we can see many teeth, we can make a reliable tooth count, and 223 is the right answer. Price had again a brilliant idea, which he'd thrown away. And he threw it away because of his differential. Now, let me put that into our gear diagram. There's the gear pair there. We need to turn it from this little axis M here, and now we can start to calculate how fast these gears turn. We know already how fast axis M turns. It's this bizarre fraction with the number 53 in, which you'll remember, which cancelled itself up in Wright's gear train. We calculate how fast E3, E4 turn, and we get this rather strange fraction, 9 times 53 over 223 times 19. But it will turn out to be a very significant ratio, as we'll see. The next gear in the train is another gear with 53 teeth. And by this time, I was getting extremely disturbed by all of this, because again, the 53 is cancelled out. It's not used in this gear train. If we look at what we need, sorry, just to say, this is the gear, reliable count says 53 teeth. So it was correct. If we look at the gear train, we don't want 53 in the final answer. We just want, it's a 4-turn dial, 223 months, 235 over 19, that's the metonic cycle. That's the ratio we want to turn our Saros pointer. We don't need this extraordinary, bizarre, strange and disturbing prime number 53. So that's what we want for the Saros pointer. This gear E3, this large gear, found no role in any previous model. Now it has two roles. It has one role. It has an essential role in turning the Saros pointer. So everything now seemed to be going on the right lines. In our modern X-rays, we can see all these gears except for the conjectural one. All the tooth counts check out. It's a completely established part of how the Antikythera mechanism works. And so this was a nice story. I had the dial, I had the gearing, but I also had a huge problem, which is if you look at the back of fragment A, inside the large gear E3, there's another couple of gears there. They were part of what Price referred to as his differential system, which I was sure by that time was wrong. And I'm going to look at them more closely, and I'm going to examine them with our X-rays. Now, if you look there, the gears on the left look like they're the gears on the right, but they're not actually those gears. I have to come forward a millimeter towards us, and you see then two more gears, and these are the gears on the right. There's 4 gears in this system. To Price's great credit, he saw that. And I want to look at the bottom gears, which are epicyclic gears, K1 and K2. and a particular feature of K2, which is very evident there, which is that it's got this notch out of it. Now, this was noticed in 1902, very early on, by Rados, but he didn't understand it. It was noticed by Price, who thought it was evidence that a tooth had broken, had been repaired, and the repair had dropped out. But Michael Wright, with his new X-rays, made a far more acute observation. He said that there's a pin on K1 which engages with a slot on K2, and in that way, gear K1 carries gear K2 around. Now, I think most people's reaction would be that this is an entirely useless idea. The gears will turn with the same speed, and you might simply just as well attach them to the same axle. But Wright made another really astonishing observation. He said that the gears turn on slightly different axes, slightly eccentric axes. The difference in the centers is just about a millimeter. And this makes all the difference. I want you to forget for a moment that these are epicyclic gears, and I'm going to show you a little animation that shows what this system does. I'm going to imagine that K1 goes round at a constant rate of the mean sidereal month. That's the gear with the pin on there. You can see K1. And on top of it sits K2. And as the gears turn, you'll see sometimes K2 is behind, and sometimes it's ahead of the pin gear. The slot gear is, you get this little variation in the motion of the slot gear. Notice that in this fixed axis situation, the period of rotation of the slot gear is the same as the input period, the sidereal month, and I'll come back to that. So going back to our actual mechanism, the key question was, could this model the variable motion of the moon? Wright considered this in a rather throwaway paragraph in one of his papers, and he discarded the idea because in his model of 2005, this large gear E3 rotated much too fast, 60 times too fast, for this to work in any meaningful way. He rejected this idea for exactly the same reason that Price rejected the idea that E3 might have 223 teeth. The gear E3 turned much too fast. But in my developing model, E3 turns, you remember, the Saros dial, which is a dial which has a period of 18 years over a 4-turn cycle. Everything's very slow, so it's going around very slowly. So maybe this is a promising idea. The second key question is, why is the pin and slot mounted epicyclically on E3? And I'm going to explain why that is. And I'm going to revert now to modern astronomy to talk about the reason. This is the lunar orbit, and it's an ellipse, as we know in modern astronomy. I've exaggerated the ellipse there very much. It's much more like a circle, but it is elliptical. Apogee is the point when the moon is furthest from the Earth, and perigee when it's closest. Apogee is when the moon appears to be going slowest against the stars because it's furthest away, and perigee when it's going fastest. And I want you to imagine the moon starting at a prominent star, which you can see on the right, going all the way round the zodiac and back to the same prominent star. This is the sidereal month, which we've talked about, period of about 27.32 days on average. Now, you might think that the moon then had got back to its slowest motion at apogee. But in fact, that's not the case, because the apogee has moved round a little bit in the meanwhile. The so-called line of apsides that joins perigee and apsides processes round in a very slow period of just under 9 years. So the anomalistic month, stay with me if you can, the anomalistic month, which is this the month of the variable motion cycle of the moon is just a bit longer than the sidereal month, only about 5.5 hours longer. Remarkably, the ancient Babylonian astronomers knew of this difference between the sidereal and anomalistic month, as did the ancient Greeks, but none of them knew about elliptical orbits. But the ancient Greeks were brilliant geometers, and they had a very beautiful theory for explaining this anomalous orbit of the moon. They said you can explain it as the sum of two simple circular motions. There's a large circular motion with a period of the sidereal month on which, and a little epicyclic added circular motion with the period anomalistic month in the opposite direction. Now that's all a bit of a mouthful, so I'm going to show you an animation of this theory. The pink dot is the actual moon, and it traces out an orbit which is like a squashed off-center circle. Each time it's slightly different as it goes round, and each time it takes a bit longer than at the sidereal month to get to the red line, to get to apogee. Sometimes the moon is behind the average moon, and sometimes it's ahead of the moon. And it models the elliptical theory, the modern theory of the moon, in a very beautiful way. Yes, the red line there is equivalent to the line of apsides of the orbit. That's the one end is where it's furthest from the Earth, and the other end where it's closest, where it appears to be moving furthest. So this is the ancient Greek epicyclic theory of the moon. Very beautiful theory. And I'm going to return to my mechanism now to ask some questions. And the key question is, how fast must this large gear E3 rotate so that this little pin and slot device exactly models this ancient Greek epicyclic theory? You remember that its basic input needs to be the sidereal month, but the period of variability needs to be this other slightly longer month, the anomalistic month. And I have to say this indeed easy. If you're encountering this for the first time, it may be you're not following it in total detail. I want to give you a flavor of what the thinking was. So the question then is, how fast should E3 rotate to make this pin and slot exactly be equivalent, geometrically equivalent to the epicyclic theory of the moon? And the answer turns out to be that it must rotate at the rotation which is the difference between the sidereal month and the anomalistic month, equivalent in modern terms of the rotation of line of apsides, this slow rotation with a period of just under 9 years. Now we can calculate this from the Metonic and Saros cycles. I'll let you do that as a little exercise to do at home. I don't really have time, but it's simple arithmetic. And when we do that simple arithmetic, we come out with this fraction 9 times 53.
You already did, Carla, as soon as I went into the kitchen.
You'll remember we already have as the rotation of E3 when we were calculating the gearing for the lower back dial, the Saros dial. So now we understand what the 53-tooth gear is doing there. It's turning E3 at exactly the right rate so that the pin and slot models this ancient Greek theory of the moon. It is, I have to say, extraordinary. Now, E3, it had no role in any previous models. Now it's got 2 roles. It turns the Saros pointer, and it carries epicyclically this little pin and slot device to model the epicyclic theory of the moon. Let me put this together. That's E3 rotating at this rate, with a period of just under 9 years. You remember.
I'm gonna pause it for just a second, but the reason why this is so important is depending on where you are for parity and apogee, that's the difference between an annular eclipse and a total eclipse. So you have to line everything up, and you have to be at the right position in the precession of the apsides in order to guarantee that your apogee and perigee will cause a total eclipse. So it's actually very important in the calculation. It seems like a lot of work to do, but the Greeks understood this, and they actually built a geared mechanism that solved this problem, which I just thought was amazing, which is why I so wanted to duplicate it in Lego.
This is little metonic gear train on the little, which output on a little regular pentagon with a hole through it. This calculates the mean sidereal month. Let me show you this in close up. There's a gear with 50 teeth sits on there, meshes with the pin gear, which also has 50 teeth, on which sits the slot gear with 50 teeth. And this generates this variable motion, and then it transmits it back, reversing its direction, onto another gear with 50 teeth.
Now, I couldn't do this the same way they did. The ancient Greeks have two pairs of 50 teeth gears that have different rolling diameters, which means the tooth pitches of these pairs are different. They're not the same tooth pitch. In order to keep my standardized Lego tooth, I had to do two 56s and two 54s. And I had to choose a dimension such that the off center, they had a 1 millimeter offset. I defined a Lego sized offset. I chose a quarter of a stud. I moved it a quarter of a stud. I normally go half studs, but I went a quarter of a stud. And a quarter of a stud is 2 millimeters in Legoland. So my offset's twice as big. And I managed to make this all work out with two 56s and two 54s with slots and pins. So
to summarize this system, we have the pin and slot mounted epicyclically to change the period in which it delivers its variation from the sidereal month to the anomalistic month. It is a truly astonishing system. I would say a shocking system. It's, in my view, an incredible idea. It's a work of absolute genius. And realizing that this is how it worked, a whole cascade of consequences came out then, that all the tooth counts could be explained from the metonic and Saros cycle. There's often in science, you make a breakthrough and everything else follows from it. It was a fantastic feeling of discovery. But we hadn't really quite finished there. That's the same gearing seen from the side. You can see the output, which calculates this variable sidereal month there. And I'd assume, like everybody else, that the gearing at the back of the mechanism went off to the left to the back dials. But this didn't seem to make much sense. And then 2 or 3 weeks later, I got a call from Mike Edmonds with a very nice insight. He said, what if the output went the other way through the little hole, you remember, in the pentagonal hub? We can see all this stuff in our x-rays, I should say. It's not made up. And the output went up towards the zodiac dial at the front of the device to show the position of the moon in the zodiac. That's where you want this sidereal month output. You might consider that this was a completely crazy thing to attempt in ancient Greece. But the craziness of the designer didn't stop there. The designer added another little device on the end of this output. And I'm going to show you that from another angle. And it shows the phase of the moon. This was a discovery by Michael Wright. And I want to take the cover of this off to show you how it works. It's just got 2 little gears in it. It's got an epicyclic crown gear with 20 teeth, which meshes with another little gear with 20 teeth on the solar output of the device. And it's a differential device. It calculates the difference between the sidereal rotation of the moon around the Earth and the rotation of the sun around the Earth, the annual cycle of the sun around the Earth, to produce the phase cycle of the moon. Now, where have you heard that before? That was what Price's differential did, what Price's brilliant differential did, but he got it in completely the wrong place with this cumbersome system. The genius who devised this device, just two little gears, which did exactly what Price's differential did. I just want to put all this together to show you how the gearing relates to the fragments and what the whole thing looks like. This is the back of fragment A. These are the gears at the back there. You can see the pin and slot there, the gears for the top dials and for the bottom dials. These are the fragments that show the back plate of the mechanism with the twin dial system, top and bottom. We come round now to the front of fragment A, and you can see these rather mysterious fingers that point up from the main drive wheel, which we believe are part of a conjectural planetary system, first proposed by Michael Wright. This is my radically simplified gearing for it. And it ends with Wright's proposal of 8 coaxial pointers showing the date, the sun, the moon, and all 5 planets known in the ancient world. This is fragment C, and it comes from all over the front of the mechanism. Quite a jigsaw puzzle to sort out. The middle part of it shows the moon phase device. Then there's the zodiac and calendar scales, and all these plus these little fragments here show REM's parapegma at the top, the star calendar at the top and bottom of the device. Everything in a wooden box turned by a little knob or crank at the side. If that doesn't shock you, I don't know what will. So that's what I'm going to say about what. And I've got some short sections now to further explore the identity of the mechanism and what.
We're going to skip over a lot of this. Now, I don't know if we're very short on time. I could cut it off here, but we're there at the big reveal at the end will get lost. Do you want to weigh in on that?
I'm for the big reveal myself.
Keep going.
Keep going. Okay. All right. Well, we'll get to the big reveal here. So we're going to skip over where. That's a wonderful discussion, and we're going to go right to when. Let's see if I can't. Past all this. All right. We'll get a little bit of the
information from that about the date of the inscription. They notice things like the omicrons are all small. The pi's tend to have their second leg shorter than the first, and the top and bottom strokes of the sigmas are splayed. Now, I have to say this process is a bit more an art than a science, and different epigraphers disagree. Let me put some information about different epigraphers' views on our timeline. Wilhelm, in the early days, probably wisely gave a rather wide range. Merritt worked with Price and said basically 1st century BC, which agreed with Price. He says the subtitle of Gears from the Greeks is a calendar computer from about 80 BC. And he had an argument for saying it was made in 80 BC, which I think all of us now believe is spurious. Kritsas worked with our group and brought the date considerably earlier. And I've worked most recently with Charles Crowther, a brilliant epigraphist from Oxford University, and he's brought the date even earlier. But we'd still like a firmer date. And some information comes out of the astronomy. Remember REM's cycles that he identified in this fragment? Well, the latest of these is the Calippic cycle, launched on a very specific date in 330 BC.
I do want to say that the 223 tooth gear, if you watch the whole Nova, if you watch this whole thing, these numbers aren't imaginary. The actual writing says 223 months of the Saros cycle. It doesn't say Saros cycle, but it is 223 months of the cycle we call the Saros cycle.
See, So this gives us a terminus post-quem for the mechanism in 330 BC. Let me add that to my timeline. There it is. Not a huge advance here. But there's more in the astronomy than that. You remember that it took 4 generations of researchers to work out this, that the mechanism exactly models the ancient Greek epicyclic theory of the moon. And the 2nd century AD, Ptolemy attributed this invention of this theory to Hipparchus of Nicaea, with those dates there. But Apollonius of Perga, it's known, developed epicyclic theories of the planets, and he was said to have been called Epsilon because the shape of an epsilon is like a crescent moon because of his work on the moon. So it seems very plausible, even likely, that Apollonius might have developed an epicyclic theory of the moon. So let me add that to our information. Depends who you believe invented this epicyclic lunar theory. So that's where it remained until a year or 2 ago. Some quite astonishing work by an Argentinian researcher, Christian Carmen, and James Evans from Puget Sound University. And they presented this work at a conference in Leiden in the Netherlands. And the arguments were so difficult, I have to say, based on complicated aspects of Babylonian eclipse prediction practice, many assumptions, and I think most of us got lost. I certainly did around a third of the way through or before then. So when they announced their result, which was astonishing, I think they must have been disappointed with our reaction. They said that they'd sequentially eliminated possibilities to determine that the full moon of month 1 of the dial is May the 12th, 205 BC, not only 100-year range for them, a particular day on which the Saros dial started. Now, I got lost, even though I'd been studying this dial pretty intensively, and I'd been looking at the times in the glyphs, the eclipse times. And I believed that these times were not based on observations by the Greeks or even a set of earlier observations by, say, the Babylonians. I believe they were generated by a simple mathematical model using the methods of the time. And I developed a mathematical model for determining these times. And it's quite a good model. It's not, unfortunately, an exact model. I'm still working on this. But when I synchronized this mathematical model of the eclipse times with the astronomy, it produced a unique fit that the full moon of month 1 of the dial is May the 12th, 205 BC. I was completely astonished by this. My methods were very different from Christian and Jim's. In some ways, our assumptions were contradictory, and the date was exactly the same. Now, I'd like to say with confidence that I can tell you this is the right date, but the truth is, I believe this is the right date, but we haven't yet resolved what's going on here. It's very difficult, I have to say. The 2 papers are there. Anyone's welcome to read them and try and sort it out, but I'm still working on it. I'm still working on this eclipse times model, which I've slightly improved, but I'm looking for an exact model. If they were using a mathematical model, it should give the exact results, and I've failed so far. Most of scientific research, as you'll know, is about failure, really. It's only occasionally that you get successes. So I don't think we've done enough yet to persuade you as the academic community that this is right. I believe it's the right date, and it's a very interesting date. Let me put it on my timeline. It agrees with the archaeology, it agrees with the epigraphy, if you agree with Charles Crowther. It agrees with the epicyclic lunar theory, if you think it was invented by Apollonius or his contemporaries or even earlier. And it's a very interesting date. It's much earlier than any previous date. The earliest previous date suggested was 150 BC. general consensus is about 100 BC. And I think it's a very interesting date in terms of the next question, which is who made the mechanism? And I'm going to put up another.
So I'm going to break that here, and it goes on for more, not much longer, but goes on a little more. And you're more than welcome. I urge you watch Nova and then watch Dr. Freeth's hour-and-a-half long lecture on this. It's very dense, and he does a wonderful job. I want to point out some things. The dials that were generated on paper in PDF files that I reused Andy Carroll's dials, and I made a compatible mechanism with his. His dials are zeroed the same way the zero in the Antikythera mechanism. They're zeroed to the first full moon of January of 2001. Andy did not design and build this device on that day or before that day. He did that in 3 months in 2010. He zeroed it because it lined up the dates to make Jan 1, 2001 and make his leap years and everything else all come out correctly. He zeroed it to that intentionally. So this is the 0 point on the Antikythera mechanism. It does not mean that the mechanism was designed at that time. And it does not mean that this device was built at that time. In fact, I can tell you, and anyone who has studied this will tell you, this is not the first one. This is Rev 27B. I use the number 27B the way a computer programmer talks about the revs of software. It has no information. There's no way that this just popped out intact. This is an evolution of refinements over time. This was a very precision-made mechanism. It had been going through many generations, all trying to do the same thing, which is probably why that number is still buried into it, even if it was made 100 years later. So we know the date that was probably designed to zero to. That applies backwards from where the design could emerge. We know that that device had to sink on a ship after 70 BCE. So if it was designed some point after that, that's a range of when this actual device that we have, the only one of these that we have, and Dr. Freeth says, somebody asked him, what else could we get? And he says, more of the mechanism, but that's kind of been eliminated. They did another visit to the site in 2017. They brought up some more stuff. They found no additional parts to it. During the Nova, they talk about finding a drawer or two that had some other parts, and they actually found a couple of key pieces that were leftover fragments in a drawer inside the Athens Museum that they found in 2005. But
Kurt, excuse me, we lost your screen.
I'm sorry. Well, I can fix that. I was just talking to nothing here. Let me see if I can get I was going to bring up one of the other things here. So let me bring up, if I can. All right. Here, I was going to bring this up, make this full screen, and show you my mechanism running. I can't really show that to you with this Zoom stuff because the lighting and everything doesn't help, but I have there's a video of me giving a 15-minute long, highly condensed, almost incoherent talk about the device in a short interview. It's if you type Lego Antikythera mechanism, you'll see one with a green thing in the middle of the thing on YouTube. You can watch me talk about this device for 15 minutes. On the 223 tooth gear, the pin and slot mechanism that does the non-constant angular motion of the moon. And if we watch over here, when I crank this, you can see the pin and slot gear tracking around. And that does the non-constant angular motion of the moon. That means it models the ellipse, but the Greeks didn't know about ellipses. They just knew the moon moves slower at some times than it did at other times. They could observe it. And they modeled it by a circle on a circle. You'll notice the 223 tooth gear is moving very slowly while that's happening. Well, you'd say, well, why would they mount it out there? Because it moves. Well, in fact, that does another thing.
this 223 tooth gear is moving exactly the speed necessary to account for the precession of the lunar apsides. Because while it's doing orbits, it's not doing the orbit in the same place. The moon is slowly precessing. And that's called the precession of the lunar apsidial precession. And that speed is 8.8529 tropical years. And that map.
So there is a bigger error in the calculation of that lunar apsides than any other thing in there. It actually gets out of sync in a relatively short period of time, like 3 decades or so. So you'd have to re-zero your mechanism every so often because it will drift out. I found a simpler ratio that's actually closer to the current right answer. The interesting question here is there been a change in the precession of the lunar apsides? Do we have a measurement by ancient Greeks and Persians that's not the same answer that it is today? That's a very interesting thing. Galileo accidentally observed Neptune. Some of you may have heard this. He actually saw it as a star and he thought the star moved. They actually used that in the fact that it was long before when they helped refine the orbit of Neptune. They used that data point, and even though it had wide air bands, it helped refine the orbit of Neptune, when they were first working on the orbital calculations of Neptune. This is an interesting fact. Is the math wrong because the Greeks didn't have a good enough measurement? Or is the math wrong because the lunar apsidial precession is changing over the 2,100 years or 2,200 years since this mechanism was designed and those measurements were made? I don't have an answer for that. It's certainly an interesting question. But you saw that on my screen here. Hopefully that probably, I think, covers everything. I'm sure there's a few questions. I'll try and answer any that people want to stick around to have answered.
Okay, I'll start with one. So when we look at eclipse predictions today, or we look at eclipse tracks, if we plan on visiting an eclipse, we have a 2, 5, 6 minute event at a certain spot on the Earth. And it's going to be different times depending on where you go on the eclipse track. Does this account for your location on the Earth in any way?
No, not at all. This, the Antikythera mechanism basically says all conditions are set up to have an eclipse, and it even tells you to the nearest 8-hour increment where the eclipse will be. If that comes while it's broad daylight, you can pretty much assume you're on the wrong side of the planet to see the eclipse. Yeah, I mean, sorry, if it's in the middle of the night. Well, it depends on whether it's a lunar eclipse or a solar eclipse. It predicts both kinds. And it predicts, obviously, there are more lunar eclipses than there are solar eclipses. But once it's calibrated and swings around, it tells you when it thinks there could be an eclipse. And I know from my own device, it predicted the eclipse that occurred in South America in 2019. The device said there should be an eclipse today, and I did it the other way. I heard there was going to be an eclipse in South America. I ran the device to see if it actually had that eclipse date in it, and sure enough, it did. It had that eclipse date in it. So it knew there was an eclipse. It just knows there's an eclipse somewhere. So it's not accurate enough to actually know where on the surface of the Earth it will be visible from. But it's still a pretty amazing piece of kit. Were there any questions written in the little chat windows that we should be reading?
There were a lot of happy comments of that's really cool.
That's okay.
All right, I'll ask another question. So it's obviously shown its capacity to calculate eclipse far into the future. I'm kind of curious about if it's hand cranked, how many revolutions do you have to give it to go 1,000 years in the future?
Oh, you'd be at it a long time. My crank cranks once per lunar month.
And
So you have to crank every lunar month. To do a Saros cycle is 223 of those cranks.
okay.
So to go 1,000 years, divide 18 into 1,000 and multiply it by 223. That's how many cranks you'll have to put into it. And I guarantee you that it will begin to drift. The Lego is not that good. I mean, it's plastic, and I'm constantly changing the design to reinforce it more. I actually have the big one, the big one that's white, and I have green gears in there because they're the corroded bronze. You see, stupidness. But anyway, I find that it flexes enough, and you crank it too fast, a gear will slip by gear, and I hear it go click, and I say, "Oh shit," because you got to go and recalibrate it again when that happens. So I'm constantly redesigning it to make it be rigid everywhere I need it to be rigid at, yet have the frame be very air spacey wise, so that you can see inside of it and watch it, operate. I actually bought some plexiglass. I was going to drill holes in it and sandwich it in plexiglass or acrylic, and it wouldn't be Lego, but at least you could see the gears and it would be more sturdy. But by the time you look through 3 layers of the plexiglass, you can't see anything either. So it's kind of there's some challenge there to make it both good operating and have the visual appeal that I was hoping to get out of it. So brass is certainly a much sturdier mechanism to make it out of.
I guess that's why they went with bronze and brass at the time. There is some recreations of this. If you've looked up the fellow in Australia, Click Spring, he's not completely finished with his, but he is attempting to make his entirely as he believes it was done the old way, down to manufacturing his own files and hand filing the gears. Clearly he has more time available than I have, but it does make a note of the fact that one large gear is driving a lot of smaller gears. It's geared so that it spins up very quickly. It really does. If you're sitting there spinning the input handle, it's spinning it up very, very quickly. So it wasn't something that was designed to be cranked very, very fast. I'm guessing, am I right that a person would use this over a number of years? You would just put a little crank here or there to go and check and match the day, and then go, okay, well, wait a minute, and there's something supposed to come up a couple of months, and then you crank it for a while to get there, and then bring it back to that date, and then reset everything in 19 years. Is that correct? It gets reset in 19 years?
Yeah, it actually does. My mechanism, like the original, has another dial that goes 3 Saros cycles, and it says +8 and -8. So it's 0, +8, and -8, and that moves the eclipse on that date forward or back from noon 8 hours. And so it switches. You'll go through a whole Saros cycle, and then you do the +8 Saros cycle, then you do the -8 Saros cycle, and then you go back to the 0 Saros cycle. So over 3 times 18 years, so the mechanism is actually zeroed on as far as the Saros cycle is concerned, over 56 years. I say as far as the Saros cycle, because you have to have the lunar apsides and the actual lunar apogees and perigees have better be calibrated, because they can drift too. And so, the whole thing probably doesn't hang together for more than about 80 to 100 years. And then there's enough air in the gearing that it will be off on the lunar apsides. It will not be calculating lunar apsides correctly. There's a lot more air in that calculation. If you go and take the number that you just saw up here in my presentation, the ratio that he showed, that Dr. Free showed, and you compute what that fraction is, and then you go look at what the real number for the lunar apsides is, and you compute the amount of air that has, it's almost an order of magnitude more air than the other numbers are. And so you calculate how often, when are you going to be 180 degrees out of phase with it, or 90 degrees out of phase, so you'll be projecting the apogee. I mean, the worst case is to predict that it's an apogee when it's perigee. So if you go 180 out, so you can calculate how long does it take that fraction, when that's calculated, over time, to be 180 degrees out of phase. And that tells you when the mechanism will definitely be out of calibration. So, you have to re-zero the device. But over the time frames they were operating in, I'm sure people were cranking it forward to see, is it going to happen in the next? I see we're coming up. They had a 5-turn dial for the calendar, and Andy did a 4-turn dial because we're used to leap years, and they had a 4-turn dial for the Saros cycle, and Andy did a 4-turn cycle for the Saros cycle, and the calculation. You can look forward on the Saros cycle, see when there's going to be a lunar eclipse or a solar eclipse, run it forward and figure out what date that matches, and then, you know, run your thing back. You know, if you're like a predictor and you want to know, hey, next spring there's going to be an eclipse, you can start, I suppose, pontificating in your temple that that's coming up. But, you know, if it's not seen in your locale, it might be seen someplace else in the empire.
So in order to make this, go ahead.
Yeah, we got a question on the chat here from Jerry. He's wondering if there's any written reference in Greek history to this device. Something unique like that, seems like somebody would have talked about it.
There is a very intriguing reference to it. There is a person who wrote an inventory of the mathematical scrolls in the Library of Alexandria. And I think his name was Tyros of Alexandria, wrote this. And in the long section of his book or treatise on the mathematical text, he lists all the works of Archimedes. And he gets to one work of Archimedes, which is called On Sphere Making. And he says, unlike all the other Archimedes texts, which are proofs, this one's on the actual construction of the devices in Greek. And we know that they called these things spheroids, you know, celestial spheres, basically. And we know that the Roman general came to Sicily, raided Archimedes' lab, and he took a couple of these back, and they were in his summer palace, and he showed them off to people, these geared, but we don't know what he had. We don't know what he had. Nobody has a picture of what he has. We only have just descriptions of these were complex mechanisms that calculated the movement of the celestial spheres. They were so, there's a caution here. Sometimes we get so wrapped up in our models and how good they predict that we think that that's how physics really works. And maybe sometimes that is true, that you can just model it better and better and you get close to how the real physics works. Or sometimes you have completely the wrong idea and the physics just behaves that way, but it has the mechanism have nothing to do with the way you're calculating those numbers. If you thought the Greeks could actually believe that there were invisible clockwork gears out there because they predicted how it worked. Clearly there was big clockwork out there. Well, we laugh at them and say they're clockwork, but we do the same thing in physics all the time and even somewhat in mathematics. Well, we have this beautiful theory that matches it and we say that must be how it is. That's not necessarily how it is.
Just to footnote, there is a reference also in Cicero when you refer to the Roman general who looted Syracuse.
Yes.
He showed his spear off to Cicero, who noted it in one of his books.
Yes, there's, I think, a couple descriptions, very one-liners that what that was, but the assumption is it's some sort of celestial sphere. They called them on-making spheres. That's what the title of the Greek scroll in the library by Archimedes. Wouldn't we love to read that? Maybe one of those toasted scrolls that they keep finding in various places that they're now being able to image them with, you know, magnetic resonance, you know, MRIs, and then virtually unroll them and then read them, you know, from the ink that's on the burnt scrolls. Maybe the computer will unfold one of these burnt, crispy, round charcoal lumps and we'll see the title of Archimedes on making spheres, and there'll be a Kurt somewhere jumping up and down in excitement that we get to read the book. But in Dr. Freeh's talk, he talks about who made it, and he lists the various candidates, or it's entirely possible that whoever made this mechanism was not the designer. And it isn't even the designer of the enhancements. It could have been craftsmen, a shop that made these things. Was there only one shop in the world? How many people worked on these over time? How many mechanisms were made? We have no clue on any of these things. Dr. Freeth asked, well, what could help? And they said, find another one. They're making huge, huge gains, and we can see example 2.
Yeah.
Coincidentally, all of that Ori stuff, which is not in my model and not in Andy Carroll's model, that's all conjecture. They have only those pins leading up in the air. None of that mechanism has survived. Maybe they were so fine that they thrown it away and fell to nothing. You know, there's speculation, and maybe good speculation, it was some sort of Ori. You know, I could build something. I could use Freeth's calculations, build something. I thought modifying Andy's to use the real prime number tooth count gears and getting the pin and slot mechanisms and getting it all to work in Lego was a sufficient challenge to wet my whistle, so to speak.
Well, for anyone who is interested in really seeing how this mechanism works, just in being able to hold it in their hand without having to spend the weeks and months building it, there are 2 apps in the Apple Store. I have them both ever since I first heard about this. One of them is called Antikythera, and the other one's called Antikythera Mechanism, and one of them shows more graphically the inside and the outside, how it works. It doesn't include the orrery, because that's later conjecture, as you mentioned. And the other one says, hey, input the date, and then it shows what it reads on all of the dials on the date. So it does internal math without all the fancy graphics. But it's a good demonstration, very similar to the graphics you showed earlier. I've watched every show on this I could get my hands on that were out there so far, and been to every site that I could find. And I still can't come up to a decision of whether to build one of these with modern Revolute gears or whether to try and stick with the more triangular shaped gears, which are clearly slightly smaller angle than an equilateral triangle is what most of them appear to be. And they seem to work fairly well if they're not heavily loaded. You got any thoughts on that?
Well, I mean, obviously, I was biased by wanting to be, I knew it wasn't going to be a pure Lego solution, because to build it with a pure Lego solution, you have to do things that they would never do, which is, you know, do subtractions by using differentials. You know, like I said, the amusing part of it is this is the first differential. There is no recorded differential older than this. This is the first appearance of a differential anywhere. Even the road measure of the Chinese is after this point in time. And so it's very intriguing to consider different ways to model it. There's some people doing it in plexiglass. I've seen somebody doing it in wood. My hope is to refine my gears a little bit more, print another one and be satisfied with them. And then maybe at Shapeways, I'll just put those parts up for sale at Shapeways, and people can print them off for the cost of, you know, producing them and get a set for themselves. But then I have to clean up all my PDF files so you can actually build it as instructions. And there's a fair amount of work in that, even though I've been working at them at the time. So, I mean, I have a lot of the data, and, you know, in my copious spare time, I hope to make a little more progress on it. And I think a number of people have used Sean Turner's and built a working Lego model matching Andy Carroll's. So I think this is a diversion from a pure Lego solution, but a nice one in that it's smaller and simpler and closer to the original.
Well done, sir. Very well done. I didn't realize you had done so many custom parts to make Lego work. Here, I was thinking, I know not everybody has a CNC or works with brass, but that's the way I was leaning about doing it, because that's what I hang around with and have. But to do it with Legos, that's pretty slick. I wouldn't have thought to 3D print it. I would have thought, okay, we'll take a piece of plastic and cut it out from that.
A lot of people doing 3D printed Lego parts now. There's you go to Shapeways, type the word Lego in there, and there are hundreds of parts now available that are Lego compatible parts. So I use the helical gears. Lego has no helical gears, and helical gears allow you to turn right angles with one shaft over the top of another. They're used in Torx differentials. Limited slip differentials have helical gears in them, so you can actually model them. And they're 1x1 stud helical gears, which is pretty cool. I've been buying them up because I'm afraid the guy will take the design down and I'll never get to buy them again.
Okay, anybody else have a question? Well, it's been really fascinating, Kurt. We really appreciate you taking the time to spend with us on this. And you got a lot of people excited judging from the comments here. So everyone's giving you a thumbs up all the way here.
Well, hopefully the math wasn't too much to get around, but if you got lost, don't feel bad about it. I assure you I was lost I don't know how many times. And it's amazing, you can read the paper and think you understand it, but then when you're faced with the gears in front of you and you say, well, that doesn't fit together. It's like, just because they wrote that's what they thought was the way it was working. But when you're face to face with the physical thing, well, is my problem because it's Lego? No, I got the same numbers as teeth that they've got. This should all work, and it's not. And then I realized that this is not right in this paper. So, it was really encouraging to see Dr. Freeth's beautiful drawings after I had built my device, but it confirmed that I had got it right. And it had to be because I could, match the predictions. I could match the eclipses that Andy had and have the pin and slot mechanisms in there to refine it. So thank you.
Well, thank you, and congratulations on the achievement too. I mean, that's tenacity to do this. It's amazing.
Well, it was a lot of fun. I really had a great time doing it.
All right, I guess we'll wrap it up then, everybody, and look for you next month when we'll have Mr. Parker from, help me out, Mike. Astronomy Technology Today. Okay.
Good catch. Thank you, Terry.
All right. Thanks, everybody, and we'll see you next month.
Good night.
Good night.
I do have a question before you end the meeting. Who would be a good person to contact just to kind of discuss the best way to take advantage of the membership? Either by phone or email.
Well, our very basic contact is email address contact@austinastro.org.
Okay.
And we'll pick up on that and we can respond to you if you need. Glad to get on the phone with you too if you aren't getting what you want out of email.
Yeah, I'd be glad to talk with you too. I think my number's available on the website.
Okay, perfect. Perfect. Thank you. Appreciate that.
Thanks for your interest.
All right, thank you.
Love your shirt, Brian.
Thank you. I finally found the manual for how to fix this thing.
Awesome. That's
Kurt,
good to see everybody.
One other